should have been a sergeant in the military because he wasn't like the colonel guy. He was like the drill sergeant guy. Like, you know how you have a job, any of you have a job to bring like the garbage can to the curb? That's your job. You forget, or are you pretty good about it?
If I forget about it, bad things happen.
Okay, these kind of bad things. Like, I forgot about it once, and I got home, and the garbage can, did I tell you this?
Yeah.
It's in my bed, and he made the sheets up over it. Like, who does that? Like, that's how I live. I was like, dude, it's not like he thought I was trying to be vindictive or defiant. I'm like, anyway, whatever. Okay, so yesterday we learned the dot product, which in and of itself doesn't do anything. Oh, look, the dot product's 12. That tells me, all the dot product is that portion, when we showed the proof yesterday, that portion of the law of cosines that I'm able to skip now. Because I don't have to find the vector on the opposite side. I don't have to find magnitudes and do all that work. I can go straight to that. It simplifies that ability to solve for the angle where I can go straight to that equation, right? Now, in that equation, I want you to notice a couple things. What if I happen to ask you, determine the angle between two vectors, and I'm not going to tell you they're perpendicular, but what if they just happen to be perpendicular, but you didn't know that, right? So I just randomly throw these two vectors out. You're not graphing them or anything. I just said determine the angle. So hopefully you know, oh, to determine the angle, I can use that angle formula, that cosine theta formula to find theta. So again, what do? You take the dot product of u and v, which is multiplying the x's, multiplying the y's, and adding them together. Now curiously, I got 0 for that dot product. Now, on the bottom, I end up doing the magnitudes, which, whatever, I got root 40 and root 160, and I put them there. And then just to show you that they're perpendicular, 0 over anything is 0, and if I took the inverse cosine of a 0, or if I look at it, what angle has a cosine value of 0? What do you say? Either 90 or 270, and honestly, if that's the two angles, I could say that it's a 90-degree angle between them, or I could say it's a 270-degree angle between them, couldn't I? All right? So the bottom line is I get 90. Now, do you think that every time two vectors are perpendicular, like they were here, or maybe not do you think, I'll just tell you, every time two vectors are perpendicular, this is going to happen. You're going to get a 0. And if I'm going to get a 0 on those, is there a shorter way than all of this to check the angle between them? Well, if you're checking for perpendicularity, all you really have to do is check the dot product. And if the dot product of two non-zero vectors is 0, right? Remember, 0 vectors have zeros there, but if they're not 0 vectors, when you take the dot product, you get 0, and you could skip all of that and say, oh, well, they must be perpendicular. I don't have to go through that entire process. Well, on your test, you're going to be asked, like this question will be asked at least a couple times. Determine if the following two vectors are parallel, perpendicular, or neither, and if they're neither parallel or perpendicular, find the angle between them. Well, if you wanted to, you could always use this formula to find the angle. And if you find the angle and get 90, you could go, oh, that must mean they're perpendicular, right? If you find the angle and you get 0, what does that mean? They're parallel. What if you find the angle and you get 180? What does that mean? They're also parallel. They're just going in different directions, right? You follow me on that? So you could always, and then if you don't get 90 or 0 or 180, then it must be some other angle between them. So you can always use this, but I like to do two quick things. I like to really check the dot product first, since I'm going to have to use it anyway. And if I happen to get 0, I go, okay, great, they're perpendicular. And I can skip all that other stuff. And then to check if they're parallel, to keep from, again, having to find magnitudes, having to do an inverse cosine. The parallel is kind of nice too, because parallel, if you think about it, you know how vectors move like x, y for your vector? So maybe this movement is 2, 4. So my vector was 2, 4. Well, what if the movement was 3, 6? If the movement is 3, 6, that's still going to give me that same direction, right? Or maybe -3, -6 would give me an opposite direction. Point is, they're parallel, aren't they? And if you look at these, vectors are going to be parallel if they're scalar multiples of each other. Now that may sound fancy, but all a scalar multiple means is, like if I factored the number out of this, say 2, and I factored, say, a 3 out of this, you can see that the vector itself is the same. The only difference is they are scalar multiples. Are you with me? Well, I don't like trying to factor one to try to make it look like the other, because sometimes that's hard. I mean, sometimes the numbers it's not even gonna seem like you can factor them. So a little trick down here, and I'll come back and talk about that orthogonal. A little trick to deciding if they're parallel is if they are parallel, you should be able to put 2 over the 3 and put 4 over the 6, or basically think of it as one vector over the other vector, and if these two fractions are equal, they're parallel. And if they're not equal, they're just not parallel, and you have to go and find the angle the other way. So I can do that check really quickly. I can do the dot product. If it's 0, I'm pretty confident it's perpendicular. If they're fractions of one over the other, and this keeps you from having to actually go and try to factor something, if you put that over that and that over that, if those are equal to each other, you know they're parallel. 2 quick checks that you can do. Are you with me? Okay, now you're going to have to do that. I'm going to run through all these things that we should know at this point. But so even something like this, which you might not have noticed, I mean, this one's not that bad. If I had to pull out a -4, I get 6 -4, scalar multiple. But if I put 6 over -24, -4 over 16, I get -1/4 for both. Or if I put that over that and that over that, I get -4 for both. If they match, I know it's parallel. Now I want to go talk about what I talked about with perpendicular a little bit more, because this is kind of a big deal. I mean, not a big deal in like the whole scheme of life, but a big deal when it comes to me asking you a couple questions on this test. People get sloppy and they say, oh, well, you just told me if the dot product of the 2 vectors is 0, then it must be perpendicular. Well, what if one of the vectors is the 0 vector? Like, what if I said, what's the angle between these two? And you said, well, I took the dot product of that, and 0 times that was 0, and 0 times that was 0, and I added them together and I got 0. It must be perpendicular. Well, the problem with that is, what is the 0 vector even doing? Does it even have a direction or a length? So how do I find the angle between it and some other vector when the 0 vector doesn't even look like a vector? And think about what you learned yesterday. How do you find the angle between any vector anyway? You do inverse tangent of y over x, right? Well, a 0 vector, 0, 0, would be inverse tangent of 0 over 0. Doesn't even make sense. So the bottom line is, I can't say that they're perpendicular if one of them doesn't even have a direction. So the flaw in that statement, if the dot product of 2 vectors is 0, they're perpendicular, is broken by this. So literally, mathematicians made a new word, orthogonal. Or orthogonal is what I normally hear from students after they forget me saying it. But orthogonal accommodates that. It basically says, if 2 vectors are not perpendicular, but if 2 vectors are orthogonal, their dot products are 0. And it's kind of like a safe bet. So if I say orthogonal, then that means perpendicular as well when they're not 0 vectors, but it also accommodates that if one of them is a 0 vector, or both are 0 vectors, I can still say orthogonal. So it's kind of like just a safe place, okay? So on my test, I ask it every year, if 2 vectors are dot product is 0, then the 2 vectors are blank. And half of you say perpendicular. And that's true as long as they're not, either of them are not 0 vectors. But if there was a 0 vector, I can't say perpendicular because there isn't an angle between them. But you can say orthogonal. Are y'all with me on that? So just think of orthogonal as kind of a safe bet. When you need to say perpendicular, you can always say orthogonal. But don't forget that perpendicular does mean something. If they're not 0 vectors, perpendicular is fine. Are you with me? So anyway, make sure you look at that. I talked about that yesterday. Anyway, and then also, I did give you a situation where if I ask you if they're parallel and I give you 2 vectors and you do the little fraction thing and you see 1/4 equals 1/4, they're definitely parallel. But if I asked you what was the angle between them, parallel vectors could have the same direction, right? If they're same direction, there's no angle between them. But they could also have opposite directions, which would mean the angle is what? 180? Is it easy to tell if they're same or opposite? I think so, because if the signs are the same, that means I'm going right down, right? Right, and then down. Well, that should be a 0 degree angle if they're parallel. But if I'm going in opposite directions, right, left, down, up, right? But I still get the same fraction there, then that should tell me opposite directions, the angle between them would be 180, not 0. Are y'all seeing that? Yes, no? Okay, so these are the kind of questions that I'm going to be asking. This test really, there are a couple times, there's one process I'll show you in a couple days that's a multi-step process, but most of these things are just regurgitating information. You can really study well for this. It's not like that trig identities test and you're like, how do I even study for a proof? I have no idea what he's going to throw at me. And you have all these guidelines to kind of try to bail yourself out. This test is very straightforward. You got a really good shot at doing well on it if you know your stuff. All right, so really quick, run through this and then we're going to talk about three-dimensional vectors, which is very little change in what we do. So real quick, if I gave you A and B, and I might not simplify all these, but I'll get you started. If I give you A and B and I ask you for vector BA, now BA means I'm starting with what? And I'm ending at A. So A is my terminal point. How do I find the vector from 2 points? What do? Terminal minus initial. But it's important that you recognize that A is the terminal. Are you with me? I'm ending with that because the arrow is pointing that way. The arrow always points to the right on vectors. And it's actually not an arrow. It really looks like that. So I'm going to take the AX value, 2, and subtract the -4. So 2 minus the -4, 6. I'm going to take the A value, -3, subtract the 7, -10. On this test, half the people I see on this easiest problem, I think, write -610 because they're just not paying attention to how I wrote this. You got to really pay attention. I'm going towards A. A is where I'm terminating. And then if I ask you magnitude, what are we doing? Square rooting the squares of each of these. Now every year I see somebody do this. -7 squared plus 3 squared, and they type that in their calculator, and they get -40. But I'm not squaring the 7 and then negating it. I'm squaring all of that. So 49 and 9 is that, right? So be careful about that if you happen to have a calculator. And you might not. Right here, find the direction angle of this. How do I find a direction angle? Not an angle between two vectors, but a direction angle. What do I do? So the direction angle of V is, that's right, inverse tangent of y over x, right? Just like regular tangents, y over x. So 3 over the -7. Now, if you didn't have a calculator, could you leave it like that? Now, you can leave that part like that, but what have I omitted? What have I forgotten? Why do I have to add 180? Because inverse tangents always give you an answer that's in the first quadrant to the fourth quadrant, right? In there? But we know that I'm going left up. That's second quadrant. So this is actually going to spit out a fourth quadrant angle, like a negative something. I don't want that. So I add what? 180. So bottom line, if that's negative and the x, you got to add 180 to put this value that you get in the correct quadrant. Now I said, what's another way to write 5 -3? 5i minus 3j, and what is this form right here with the brackets called? With the brackets. Component form, and this is called unit vector form. You got to know that because I'm going to ask you these things. So again, if you don't know those things, write those in because that's a gap in your understanding right now. Is there another way to write a vector that we've talked about a little bit, but not much? Okay, so I could use magnitude and direction angle if I wanted to find that magnitude and put it out front, and then big parentheses. This is trig form, and then you'd have cosine of the direction angle of that, whatever that is, I plus sine times the direction angle j. And we're going to talk about more of that later. I think actually on your assignment sheet last night, I was looking at this, and on the assignment sheet it said trig form of a vector worksheet. I have no idea why it's there. Maybe it's I just noticed that last night. You'll see again that trig form of a vector worksheet shows up. It showed up somewhere else. Yes, on Thursday. vector word problems with trig form of a vector worksheet. That's when we're gonna actually cover them. So if you happen to see that and were wondering what the heck that was, don't worry about it, just draw a line through. We're not covering that yesterday or today. All right, what about this? If you have an angle that's 35 and the magnitude is 10, how would you find the components to get into the component form? I gotta put it in component form right here. So what do I do for component form? How do I find x, the x movement? All right, everybody needs to have a star. If you don't know that, put it on there, because that's like the first thing we talked about. We got to do what? 10 times the cosine of 35 degrees, 10 times the sine of 35 degrees. And then you simplify that with your calculator to get your components, which I'm not going to do right now. And if you didn't have a calculator, you would just leave it like that, because I don't know how to deal with 35. And if you really think about it, this is like me putting it in trig form and then just multiplying the magnitude in, right? Magnitude cosine theta I, magnitude sine theta j. So if I did that and multiplied it in and then just dropped the I and the j, put a comma in a bracket, I would have a component form. And a vector is a quantity that shows both magnitude and direction. And scroll on up, number 7. It says if V and W are this, can I find 2V minus 3W? Okay, a lot of people know what they're doing here, and sometimes I'll say, I'll give you V, I'll give you W, and then I'll say find 2W minus 3V. And I'll switch the order. It's not a big deal, but it's something that people actually miss. So be careful, twice the V minus 3 times the W. How do I do this? Essentially distribute that in. I'm going to distribute the whole -3 in, but if I do that, what do I need to do in between these then? Add. So when I do that, I end up with the -9, -25. Now, how do I find a unit vector? We talked about that yesterday. A unit vector is not unit vector form. Every year I have somebody go, oh, unit vector form, 5i plus 12j. But a unit vector doesn't even have to have unit vector form. It just has to be what? Have a length of 1. And right now I've got a length of 13 if I did the magnitude on this. So how do I make a unit vector out of a bigger vector? Divide by its magnitude. And guys, you've done this. Do you remember what you learned about a 30, 60, 90 triangle in Homer's class? What did you learn about the sides? What was the proportion? No, that's the angles. What was the proportion? You learned 1a, 2a, a root 3, right? Are these the things that we did on the unit circle? Is that how we labeled stuff on the unit circle? What did we do? We wanted the unit circle to have a length of 1, right? So what did we do? We divided everything by 2, which is the length or the magnitude, right? So all I did was divide everything by 2, and that's where we got our root 3 and our 1/2 and our 1. Well, that would be like a 1 unit vector. So divide by the hypotenuse length of the magnitude. That's all I'm doing. So if the magnitude of V, when you calculate it, here I just know it's a triple, so I know it's 13. But if the magnitude, find it, and then just divide every component by it. And that would be your unit vector of V. And if it happens to have a magnitude that's a radical, make sure you do rationalize. Are y'all seeing that? So what that does is that takes a vector that has like a length of 2, and it shrinks it down to a smaller vector, but still in the same direction, right, that has a length of 1. That's what you're doing when you find the unit vector. And then to find the dot product, what do I do? Yeah, on the test, I see this all the time. People are used to adding, by adding these and ending up with a new vector. So they think, oh, well, a dot product means multiply, and they write it as a new vector. You're getting no credit for that. That to me is somebody who hadn't done anything, hasn't done any homework, and they just go, really has done nothing, because we're going to talk about this so much. And just is like, well, I don't know, I'm just going to wing it. So I'm not going to give you credit for, oh my gosh, what a great job, you did multiplying 5 times -3. None for that. So make sure you remember the dot product adds those values when we're done. And that value in and of itself doesn't mean much, right? But it does represent a very simplified portion of the law of cosines, which is going to help me maybe later, like on number 10. So how do I find the angle between the vectors?
Dot product over the magnitude.
Now, I always hear, and I think I heard it just a second ago, dot product over the magnitudes. But that doesn't give me the angle, that gives me the cosine of the angle. So make sure you're careful about that. I actually see people do that a good deal. They say, all right, the dot product of u and v, magnitude of u, magnitude of v. So the dot product ends up giving me 2 times 1, -3 times -2. So that ends up giving me 8. The magnitudes end up giving me 4 and 3. I'm sorry, 4 and 9, 13, and 1 and 4, root 5. I'm just going to put both under one big radical. And you can multiply those together if you want, but most of the time it's going to be a calculator problem, so I really don't need to risk anything. But if I just write that and rationalize, by the way, don't ever rationalize this. You're going to put it in your calculator at best, right? So that isn't the angle, that is the cosine of the angle. So at this point, if I have cosine of the angle equals 8 over root 13 and 5, how would I solve? Inverse cosine of all of that. So if I didn't have my calculator, again, just leave it like that. And do I ever have to worry about adding 180 here? Why not? Say these are my two angles, right? U and V. Because what? Somebody was about to say it. Because inverse cosine is defined between 0 and 180. And one of these angles is going to be between 0 and 180, right? I can't, one of them has to be an angle smaller than 180. It's just, or unless they're actually equal to 180, and that's fine. But I would know that if they were parallel. I could do my little parallel check, probably save a little time. So anyway, you don't have to worry about ever adding 180 on this. Are you with me? So far so good? Okay, indicate whether they're parallel, perpendicular, or neither. How could I do a quick parallel check on this? Parallel check. Okay, so put that x over that x, that y over that y, and I get -2/3 and -6. Are those equal? No. Well, then they're not parallel. Okay, well, how would I check for perpendicularity? Or orthogonal, or whether they're orthogonal? Dot product gives me -24, and then another -24. And when I add those together, I get -48. So it kind of looked like it might be, but the signs were the same. So that's not equal to 0, so they're not perpendicular. So in this case, they're neither parallel nor perpendicular. And if you wanted to know the angle between them, you'd have to check your cosine theta formula, wouldn't you? Are you with me on that? And those checks don't take any time to do it. It beats doing the cosine of theta and then looking at the answer to see if they're parallel, I think. What about this one? Are they parallel? Let's check. -6 over the 9, -4 over the 6. Both of those simplify to -2/3. Yes, definitely parallel. But over here, neither. And if I asked you what was the angle between these on B, what would you say? 180, because they're going in opposite directions. If they were going in the same direction, you can see that from the signs, right? Left down versus right up. So if they're parallel, same exact signs, that tells you go in the same way. If they're opposite signs, that tells you go in the opposite ways. And that's how you can determine whether it's 0 or 180 from that. What about this? Find a vector with a length of 8. Now this is not something we've done, but I want to see if somebody can rise to the challenge here. How do I find a vector with a length of 8 that is in the same direction as this? Because this right here doesn't have a length of 8. This has a length of root 10, because that's the magnitude, right? So root 10 is a little bit bigger than 3. So I've got this vector going left 3, up 1, looks maybe something like that, and the magnitude is like a root 10, which is 3-ish. I want it to have a magnitude of 8. How do I do that? How do I stretch this back? We've already talked about how to take a vector and shrink it down to 1. How do I stretch it out to 8?
Multiply each term by 8 over root 10.
Did y'all hear that? Yes or no? Multiply each term by 8 over root 10. Do you see why that works? What am I essentially doing if I multiply that whole thing by 8 over root 10? I'm turning it into a unit vector, which is a length of 1, and then I'm doing what? Multiplying it by 8 to make it 8. That's what that's doing. Are y'all seeing that? So once you get it down to 1, you can always kind of move around and make it any size you want. All right, now granted, when I do that, I'm going to get negative 24 root 10, positive 8 root 10, and at this point, I'm going to need to rationalize and then simplify when I'm done. Are y'all with me? And remember, sometimes after you rationalize, you can still simplify the fractions. So still got a little work here. What is the magnitude and direction angle of this? Okay, every year I do this, and maybe I'm a little sadistic, maybe I'm just bored, but every year I give this question, and I don't give hardly any space on purpose. And I have people go, okay, magnitude and direction of this thing. I guess I'm going to have to just multiply it all out and see what I'm dealing with. So they go in here and they go, all right, cosine of 3 pi over 4, that would be a negative square root of 2 over 2. So they get negative root 2 over 2. And then sine of 3 pi over 4, positive root 2 over 2. And then they take this and they multiply by 6. And they get, all right, negative 3 root 2, positive 3 root 2. All right, there's my vector. And then they go, all right, now I need to find the magnitude. And they go, all right, the magnitude of my vector. And they come in here and they square that thing and they get 18. And then they square that thing and they get 18. And they add them together and they go square root of 36 is 6. Whew, got it. And then they come in here and they go, all right, direction angle. For my direction angle, I'm going to do inverse tangent. And they're going to put that, 3 root 2, over that, negative 3 root 2. And then they're going to go, oh, but that's negative. Don't forget to add 180. And they're going to go, what's the inverse tangent of negative 1? And what do? Inverse tangent of negative 1 would have to be negative 45 degrees down in the 4th quadrant. But then out of 180, and I get 135. All right, so magnitude 6, angle's 135.
Yeah.
And they got it all squeezed in there. But man, what form is this in? Magnitude cosine of the angles plus I sine of the angle. Don't do this. Okay? Every year, I literally, I'm like, okay, I'm going to do it again. I'm going to give them this question, see if they know what trig form means. And people do all this work. Now, the sad part is, people make errors in here. And they go, oh, magnitude's 12, direction angle's negative 45. And I'm like, oh, this is trig form, all right? So magnitude is that number, and those angles will match. That's the angle. Are y'all with me? So don't do this. If you do it and you do it right, that's fine, but you just wasted 3 or 4 minutes or whatever it takes you. All right, so make it easy on yourself on that. All right, okay, today we've still got 15 minutes, so I want to show you 3-dimensional vectors. Now, when I say 3-dimensional vectors, sometimes that strikes fear into the hearts of students. They're like, 3 dimensions? We've never done 3 dimensions. Literally, hardly anything changes. All of your rules you will see will hold. So I'm going to run you through these, and then you've got a little bookwork, but just watch. There's a very little difference in between this and what we already know, with this exception. When I do a direction angle, not an angle between 2 vectors, but a direction angle, what do? Inverse tangent of y over x. Well, what would you do then if you had an inverse tangent of y over x, but there's also a z component? Surely the z does something, right? Well, I'm never going to ask you direction angle with these. Because really what I would have to do is I would have multi-directional angles. I would have not just an angle towards 0, but you'd have an angle towards the z-axis, the y-axis. You'd have all these different values. We're not going to get into that in this class. But all the other stuff I can still ask you. All right, so if I ever ask you a direction angle, it'll only be with a 2-dimensional vector. Okay, and that dimension would be x and y. So with this, if I gave you these 2 points, I just have an x, a y, and a z, and I'm trying to get the vector AB. So I am terminating where? At the B. So when you find the vector, you're going to do the same thing you did before, but you're just going to do it with all 3 sets of components. So if I terminate at B, negative 1 minus the 7, negative 3 minus the 5, and then 6 minus the negative 2. And you're just going to have 3 components instead of 2. If I say find the unit vector in this direction, I tell you, before we do that, did I ask you? Oh, we'll do this. Find the unit vector, not unit vector form, the unit vector. What do I want? A vector in the same direction as this, but with a length of 1. Well, how do you think I find magnitude of a vector if it's 3 dimensions? You've actually done this. You called it a space diagonal. Remember when you had a cube and you did that space diagonal? That was literally a vector, the length of the thing, the magnitude going through the middle of that cube. Are you with me? Or whatever it was. So same thing, I'm going to square root, not just that squared plus that squared, but that squared plus that squared plus that squared. You with me? So if the length of this thing is a little bit bigger than 5 at root 26, what would I have to do to take this length of root 26 and shrink it down to a length of 1? Divide by that guy. So my unit vector would just be the 3 over the root 26, the negative 1 over the root 26, and the 4 over the root 26. And then remember, of course, to rationalize. What about this? Do you think 2v minus 3u is going to be a whole lot different than what we did a few minutes ago? Check it out. Twice the v. Now notice I changed the order on these. The v is that. 3, negative 1, 2. And then minus 3 times the u. Negative 1, 2, 0. You really think the math's that different? No, you're talking about the same thing, right? So 6, negative 2, 4. I'm going to put a plus there and move the whole negative 3 in. Positive 3, negative 6, 0. And therefore 9, negative 8, 4. And look at this one, number 4. It says find the unit vector in the direction of v if v is the vector from P to Q. I'm asking you to do 2 things. What's the first thing you're going to need to do? Find PQ. So from P to Q would be PQ. And what would I have to do first? Terminal minus initial. Because these are points, right? Notice the brackets are not around these. So I would have to go terminal minus initial, 3. Terminal minus initial, negative 3. Terminal minus initial, positive 3. And then once I have my vector, how do I make it a unit vector? I divide by the magnitude. And what's the magnitude of that? Square, 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 right? Under the radical. So the magnitude of that PQ, and they said V was basically PQ. So if V is PQ, vector V is from P to Q, the magnitude of that would be root 27, or 3 root 3. So I would have to divide everything by 3 root 3. And then again, cancel, simplify, rationalize. What about 5a? Do you think dot product is any different? Not really. Dot product, same kind of thinking. What am I going to do here? Multiply the x's, multiply the y's, but also multiply the z's, and make sure that you add them all when you're done. And again, what does that dot product mean? In and of itself, not much, but it is that portion of the law of cosines that we're really able to knock out and make a much simpler process in finding cosine, finding the angle theta. Dot product of those, what's going to happen if you're missing the j term up here? That's right, plug in the 0. So here, I'm going to have 3 times the 4 plus negative 3 times the 0 plus 2 times the 1, 12 minus nothing, or plus nothing, whatever, plus 2. Now, this one people freak out a little bit. It says, calculate the angle between U and V. Now, I made a side note. If I don't give you a calculator on your test, yes, you could do inverse cosine and just leave it like that. But sometimes, and Vestavia tournaments, state tournaments sometimes do this too. They say, find the cosine of the angle. Well, if I said find cosine of the angle, what would I just do? Just the dot products over the magnitudes and leave it. If I say find the angle, you got to inverse cosine that. So if I say calculate the angle, I'm going to have to go ahead and do the inverse cosine. If I don't have a calculator, I would just leave it with inverse cosine of that mess. So what do I have to do to find the angle? Dot product, so -6, +3, -4. There's my dot product, which ends up giving me -7. And then the magnitudes of each one would be what? 9, 1, 4. Root 14. 4, 9, 4. Root 17. So all of that gives me root whatever 14 times 17 is. And I'm not even going to bother multiplying it out because my calculator will do that. So if I asked you what was cosine of theta, you would have just written this that I'm underlining in brown. But if I ask you for the angle, which is what I did here, then I'm going to say theta equals the inverse cosine of that. Are y'all tracking with me on this? Yes? Okay. All right. And then, of course, if you have a calculator, type it. All right, number 7. Let's check it out. Which of the following is true about these two vectors? Okay, they're orthogonal. Now, could they be orthogonal? It's possible, right?
Yeah.
But how would I check real quickly? See if their dot products are 0. Okay, so when I check the dot product, I get -1, -4/9, -1/4. Well, there's no way that's 0. They're all negative, right? So right there, I'm like, no way that this is orthogonal. No, sir. They're parallel. How could I check parallelism? Divide. So what's -1/2 divided by a +2? Don't tell me -1. Because 1/2 pi divided into 2 parts is not a whole pi. So to divide by 2, I multiply by 1/2, which would give me, so that first comparison was -1/4. What is 1/3 divided by -4/3? -1/4. Ooh, so far so good. What is -1/4 divided by 1? Oh, so they are parallel. Now, if I said, what's the angle between them, what would you say? Now, if it's parallel, it's either 0 or 180.
180.
Why would you say 180?
Because all the terms are opposites.
Yeah, they're going in opposite directions, right? One's going left up into the plane, and the next one's going right down out of the plane. But really, if you get this, you know they're parallel. Just look at the signs. Opposite, that'd be 180. Same, that'd be 0. All right, and then so you don't have to really check anything. Oh, what about this though? I definitely know that they're parallel, and I can say parallel though because I don't have a unit vector, right? I mean, I don't have a 0 vector or anything like that that's messing with me. Although that'd be more of an orthogonal thing. Right, U is a unit vector of V. Now, if they're going in opposite directions, I wouldn't say there's a unit vector, would you? Because even if one is the same direction as the other, you know, I mean, that possibly, because a unit vector has to be going in the same direction. Are you with me? But anyway, actually, that's not true. I guess if I said unit vector in the same direction. So maybe, can I check to see if one is a unit vector of the other? What would I have to do to see if U is a unit vector at all? Check the magnitude. All right, if it was a unit vector, it'd have to have a magnitude of 1. When I check the magnitude there, I get 1/4, 1/9, 1/16. Does that look like a magnitude of 1? Now, I could find a common denominator, but when I think 0.25, 0.1, small, that's not equal to 1. So I'm not even going to bother trying to see if I can clearly tell that it's not. Is the angle between them 45? Not if they're parallel. Is it none of these? Not if it's B. So make sure you check all these. Maybe there's a multiple choice that more than one would work. Don't just grab B in. If it says which of the following statements is true. All right, find a vector parallel to that has an x component of -5. Now, I have not asked you this question directly, but can you figure it out? I'm telling you it's parallel. So there's another vector that has an x component of, I'll call it W, an x component of -5. How could I find that other vector that make it, but still make sure it's parallel? Do what? You could. If I multiply everything by -5/2 right there, that would give me -5, which checks that box. And we know if they're parallel, they're scalar multiples. Now I love that she can see -5/2 in there, but what if you can't? What if you're like, I don't know what that vector is? What has to happen if they're parallel? All these little things have to make little fractions that are equal, right? Right? So couldn't you just do a little proportion? You track with me? And when you do that, you get 2x equal -5 times -3, and then you divide by 2. And if you look closely, what did I really do? I multiplied the -3 by what? -5/2. All right? And then I can turn around and do it again. 2 over -5 would also have to equal -1 over y. And I could cross multiply again. And then divide by 2. But again, y, what am I multiplying that -1 by? -5/2. Besides calculating an angle between them, how do you check if a pair of vectors is orthogonal? What's our trick? The dot product would be 0. Good. Besides calculating the angle between them, how do you check if a pair of vectors is parallel? What's equal? Little fraction thingies? Why did mathematicians invent the word orthogonal? To accommodate the 0 vector, right? If a 0 vector, it wouldn't be perpendicular. And then we might run out of time on this. We have run out of time on this. So what I'm going to do is talk about this tomorrow. So if you see any of this, which I think you will, sadly, on your test, on your homework, you can ignore those. But make sure you make a note to go back and look at them after we discuss it.